This is our third video on light waves, and in the last video we introduced a little bit or touched the topic of thin film. We didn't do any questions in the last video. The description has the link for the last video for light waves video 2. So we did say in the previous video that thin film interference occurs when light waves reflecting off the top and the bottom surfaces of a thin film interfere with one another. And this type of interference is the reason why the thin films, such as oil or soap bubbles, form colorful patterns. In the previous video, I also tried to explain to you that if the light comes from the lower dense medium to the higher dense medium, when it reflects, it's reflected with 180 degree shift. And that means if it was coming this way, then it will come back shifted 180 degrees. And also we talked about that if this light wave partially is going to be reflected, but partially is still going to come into the second medium, and when it meets the next the boundary between two mediums, if it is, so if you're N1 and then N2 and N3, so if N1 is thinner than N2 and N2 is thinner than N3, here again you're gonna have 180 degree shift, and then this light that is coming out is also 180 degree shift. But what happens is all depends on this distance. If there are full wavelength of light comes out in 180 degree shifted, then you will have, like in this picture, constructive interference. So if this they call it here T, if twice the T distance happens, then you will have you have m number of wavelengths inside of that twice the T. So it's there T and back T, so it's twice the distance T. Then you will have m number of wavelengths fitting within that distance, and it will give you constructive interference. Both of them are shifted 180 degrees. But if this distance was shorter, then you would have it this much, and when the other one is 180 degrees shifted, it would come back that way, and that will give you destructive interference. So it would not be 180 degrees shifted anymore, it would be 0 degrees shifted, and it still would be shifted at the point where it's reflecting off the surface, but it will come not 180 degrees shifted, the same as the other one, and it will give you destructive interference. So for the other one, I'm going to have twice the length of it, twice there and back length of it, is equal to m minus 1/2 of the wavelength, because here you only see 1/2 of the wavelength fitting in. So it's minus 1/2 of the wavelength. And m has to be a 1, so 1 full wavelength, 2 full wavelengths. So here it's 1/2 shorter of the wavelength. But if you had the case where n1 is less than n2, and n2 is also greater than n1, then these guys shift. So wherever was destructive becomes constructive, and wherever was constructive becomes destructive. So let's look at some cases. So here you had, in this case, you had twice 180 degree shift, and in this case you will have only 180 degree shift, because if the light is coming in, it gets shifted 180 degrees. And second time when it hits the surface, because the next medium is thinner, there's not going to be 180 degrees shifted, so it will come out as 0 degrees shifted compared to the one that is coming. So again, if you want to get constructive interference, you have to make this length, half wavelength, longer, so when it reflects without 180 degrees shifted, it matches the one that was coming from the first surface reflection, and then those two wavelengths will give you constructive interference. So it will depend on the wavelength of the light that is coming and on the thickness of the thin film. And because the wavelength of the light that is coming, the visible light, has different wavelengths. You may see the red light, but you will not see the green light, because the green light has destructive interference, but the red light has constructive interference, because all the lights in the visible spectrum have different wavelengths. So you only see some lights, but you don't see others. These formulas are not given on AP exam, so you have to understand the conceptual part of it in order to be able to solve these questions. So let's look at some examples and the problems involving these formulas and how to solve them. And I should also mention in this part right here somewhere that the lambda that you see in this formula, this lambda and this lambda wavelength and this wavelength and this wavelength, it's not the wavelength in the vacuum. Remember that the frequency doesn't change when light travels from one medium to another, but the wavelength and the speed do change. So because n is equal to the speed of light over the velocity in the medium, which is lambda times the frequency over lambda times the frequency. But the one at the bottom is the lambda in the medium. So the frequency and the frequency can be cancelled. So n is equal to lambda in the vacuum over lambda in the medium. So what they mean under lambda in their formula, they mean lambda, the one that is, or the wavelength, the one that is in the medium. So that is this divided by that. So this one is not the wavelength in the vacuum, it's the wavelength in the medium. So you have to remember that when you plug in this into your formulas. Let's look at this question where they say that the light with a wavelength of 555 nanometers is incident on a soap bubble. What is the minimum thickness of thin film interference, constructive, to take place for this wavelength of light? And the index of refraction for the bubble is 1.35. So the case that we have n1 is less than n2 and n2 is greater than n1. And in this case, the constructive interference is equal to 2 times the distance that the thickness of the thin film, and equals to m plus minus, it doesn't matter whether you do plus or minus 1/2. If you choose m to be 0 wavelengths, then you add 1/2. If you choose m to be 1, then you choose negative 1/2. And lambda of the wavelength in that medium. So I'm looking for the thickness. So 2 times d is equal to, so if I choose m to be 0, then I have plus 1/2. And the wavelength in that medium is the wavelength in the vacuum divided by n. So I will have 2d is equal to 1/2. And then wavelength in the vacuum is 555 nanometers, 10 to the negative 9, that's right, 10 to the negative 9. And all of that divided by n, which they give 135. So here I have d is going to be equal to 1/4, 555, 10 to the negative 9, divided by 135, and that is equal to 102.8, 10 to the negative 9 meters, or 102.8 nanometers. In the next question, they say find the minimum film thickness for destructive interference in reflected light if the thin film, the index of refraction given 135, is illuminated by light that has a wavelength of 585 nanometers. And 585 nanometers falls somewhere right here. So it's the light green, maybe. So for destructive interference, when we have 2 times d is equal to, or 2 times t is equal to, and then I have m lambda, then 2 times, I'm looking for the thickness, and I'm looking for minimum thickness, so m is going to be 1, and the wavelength is 585 in the vacuum, but I have to divide it by the index of refraction. So I have 585 nanometers divided by refraction index, which is 1.35. So the distance minimum needed to cause the destructive interference for this light green light would be 217 nanometers. So Newton rings have the same effect as thin film, and it's the result of the path difference between the reflected ray and the incident ray, depending upon the thickness of the air gap between the lens and the base. And as the lens is symmetrical along its axis, the thickness is constant along the circumference of the ring and a given radius. So Newton's rings are circular. So here is an example of Newton rings, what they would look like. And you see that there is a gap. Remember, like when I introduced you to thin film, I said that it will depend on the thickness. So you may have 180-degree shift and another one also 180-degree shift, but if it was shorter, then it's reflected with not 180-degree shift compared to the one that was first reflected. So it depends on the thickness, and here you see the lens and there is change in thickness. So because of that thickness changes when the light reflects off the second surface, it causes these rings. I haven't seen again these formulas on AP exam, but the concept might be tested. So if you want to calculate the radius of these rings, you would have to use these formulas. So there are dark fringes and there are bright fringes, and to get the dark ones, that would be the destructive interference, you have r squared, so that's the radius of the rim. So here it would be the radius of the so this would be the little r, the radius of the circles, the Newton circles, and the big R, the uppercase R, is the one that is the radius of the lens. So let's look at some questions that involve the question related to these rings formulas. So in this question, they say in the incident light has a wavelength of 500 nanometers and the radius of curvature of the lens is given 2 meters. What is the radius of the fourth bright ring? And when they mean fourth bright ring, they mean the constructive interference, and I'm looking for the fourth one. So I'm gonna look at the bright fringes or constructive interference. So I have r squared is equal to, m is the fourth one, so I have 4 minus 1/2, and then the radius of the curvature for the lens is 2 meters, and the wavelength is given 500 nanometers. So this one is 500, nano is 10 to the negative 9. So I get r is equal to the square root of I have 3.5 times 2 times 5 and 10 to the negative 7. So that will give me 1.9 millimeter. In this question, they say calculate the minimum thickness of the soap bubble film that has index of refraction 1.33 that will result in the constructive interference in the reflected light if the film is illuminated by the light that has a wavelength of 602 nanometers in free space. And if they say in free space, that means in the vacuum. So for constructive interference in this case, it would be 2D and m plus 1/2 lambda in the medium. Because I have the soap bubble, so I will have the thicker medium and the thinner medium on both sides. So I have the first one with 180-degree shift, and the second one will have no 180-degree shift. So in order for it to stay with the first wave, it has to be the twice length there and back, has to be 1/2 wavelength longer than in order to give me another 180-degree shift. So now I'm gonna plug in the information that is given. So I have 2 times the distance there and back is equal to m is gonna be 0 because I start with addition. If it's minus, then I would have to say 1 minus because they ask about minimum thickness. So that's gonna be 1/2. So I will choose 0 plus 1/2, and the wavelength in the soap bubble would be the wavelength in the vacuum divided by the index of refraction, which is 1.33. And then from here I find that the distance needed to cause this constructive interference would have to be 113 nanometers. For the next question, they ask what other film thickness will produce constructive interference. So instead of plugging in m equals to 0, I'm going to plug in 1. Then I will have 2 times the distance is equal to 1 plus 1.5 gives me 3/2. And then 602 10 to the -9 divided by 1.33. So in this case, D would be equal to 339 nanometers. And then the next one you would have that was 1 plus 1.5. The next one is going to be 2 plus 1.5. So it's going to be 5 times bigger, 7 times bigger, and so on. So the numbers would be 566 nanometers, and then 792 nanometers, and so on. So that would be the answer for number 10. In this question, they say semiconductors such as silicon are used to fabricate solar cells, devices that generate electric energy when exposed to sunlight. So solar cells are often coated with a transparent thin film such as silicon monoxide, and the index of refraction is 1.45 to minimize reflective losses. So you see here in the picture, a silicon solar cell has the blue color, not the gray one already, has the index of refraction of 3.5, is coated with a thin film of silicon monoxide for this purpose. Okay, so assuming normal incidence, determine the minimum thickness of the thin film that will produce the least reflection of the wavelength that has the wavelength of 552 nanometers. And we want minimum reflection, so we want the light not to be reflected. So we are looking for the destructive interference. And in this case, I have the case where N1 is less than N2 and less than N3. It goes from 1 and then 1.5 and then 3.5. So in this case, for destructive interference, we have 2 times the distance of the thin film. So this would be the distance of the thin film, so I'm going to call it D, and equals to m minus or plus 1/2 in times the wavelength in that medium. So I have 2 times the distance is equal to, in m I'm going to choose 1 because I'm subtracting, so that gives me 1/2 times the wavelength in the medium. So that is 552 nanometers, or 10 to the negative 9, and divided by the index of refraction in the thin film, which is 1.45. So from here I find that the minimum thickness needed is 95.2 nanometers. I have time to cover some of the double slit experiment, and I will do it over here. We're going to derive the formula. So one of the most famous experiments in physics is the double slit experiment. It demonstrates that a little part of matter, little particles of matter, have something of a wave about them. And it also suggests that the very act of observing a particle has a dramatic effect on its behavior. So imagine throwing a tennis ball that has a hole in the wall. So let's say there's 2 holes in the walls. Some balls will bounce off the wall and some will go through. The ones that will get through, they will cause the fringes, like only 2 fringes on the wall, because this is where the tennis balls will probably hit the wall. And you can mark those fringes with the dot every single time when they hit them. So in the image, you would only see 2 stripes of the dots where the tennis ball would hit the wall. If you had a wave going through 2 holes, you would have the image of the interference where one wave is interfering with the other. And when they have destructive interference, you would have waves canceling each other. And if you have constructive interference, you would have the amplitude increase in those points. So the image you see right now, you would have with the wave where you have the pattern of interference. So what happened is they looked at the same when they took the light, and the light is made of the particles or quantas. It's a photon, or they can do the same with the electron. So when they shoot an electron one at a time, it still causes the wave pattern of interference. And this is where physicists were puzzled, because how can an electron pass through one or another slit and interfere with each other, with itself, when it passes through those slits, and cause the wave pattern or double slit experiment pattern. So what we're gonna look at is how to calculate the distances between these bright fringes and the effect of cancellation where it's the dark fringes, where the light cancels itself. And again, you have many videos in your lessons where I want you to watch more visual examples of double slit experiment, and probably more interested explanation than mine here. So let's look at how we derive the formulas, so we understand the formula, and then how we apply it to solve problems. So double slit experiment happens because when one wave is shorter than the other, it will have constructive interference when they arrive at 180-degree shift. So if one arrives here this way and the other one arrives this way, they cancel each other. But if they arrive in the same phase, they will have constructive interference. So if this point P was constructive interference, then that would only happen if this length is equal to this length. That means this part has to be, and they call it delta, must be number of the wavelengths of the light that is coming. So if there is like 1 wavelength, or maybe 2 wavelengths, or 3 wavelengths, or 4 wavelengths difference between these 2 arrays, then you will have them in the same phase, because this part is going to be in length equal to this part. So you can have constructive interference when this phenomena happens, or this case happens. So this is the distance, how far you will have this bright fringe from the center line. And if I look at the blue triangle, I will clear it a little bit. So if I look at the blue triangle, this is angle theta, and tangent theta from this triangle is equal to y over the distance between the two fringes, the double slit and the screen. So I'm gonna call it L. So that is the distance from here to here, that is L. And because this angle theta is very tiny compared to like it's a very small angle, and because this distance, it can be maybe a few millimeters, and this distance can be a meter, so this angle is very small. Now if I look at this triangle, the distance right here is the number of the wavelengths, maybe 2 wavelengths, 3 wavelengths, 4 wavelengths, 5 wavelengths, and so on. But the wavelength of the light, visible light, is in nanometers, so that number is very small. So because this number is very small, and the distance between the fringes is also in millimeters or micrometers, so this distance is also very small. So that means this angle is also tiny. So I have two angles that are very tiny. I'm going to write the expression for this angle. So I'm going to call this angle theta as well. And I'm going to say sine theta is equal to, and its opposite, which is m times lambda, over the hypotenuse, which is the distance, because this is the right angle. If you take your calculator, I want you to choose an angle that is very small for both tangent and sine. So if you say sine of 1 degree is equal to, and tangent of 1 degree is equal to, this is what I get. So for the very, very small angles, your sine is equal to tangent. And this is where they switch their calculations, and they say if your tangent is equal to sine, then the y over L is equal to m lambda over d. So, and here is the formula for double slit experiment. So y over L is equal to m lambda over d. If you understand this formula, you can derive it yourself. And on AP exam, it's not given in this form, but it's easy to understand and derive. So I'm going to rewrite this formula also this way. Y times d is equal to m lambda L. So one or the other way you can write this formula. And I'm going to stop my video at this point because I only have 1 minute left before the video runs out of time. And I will do more questions related to double slit experiment in our next video, which is going to be light waves video 4, and the link is in the description. Thank you for watching this video, and I'll see you in the next one.